Okay. Thank you very much for the introduction. And I need to thank all of the organizers for inviting me and giving me this opportunity to talk in this so far very nice conference. So today I'm going to talk with this title, but because this is I need to give this talk in front of many mathematicians. Last week I asked a certain person who happened to visit IIS if this talk will be understandable to mathematicians, and he said no. In fact, I need to change the title a bit because apparently it doesn't really form a TQFT in the usual definition. So I need to change the title a bit. That will be on 2D TQFT whose values are holomorphic symplectic varieties. So I need to slightly weaken the definition. So now it's collaboration with Greg Moore. So you know who I talked to last week. So I'll give a mathematical reformulation of the known results in string theory, which was found in the last few years. So it started with Argyris-Seiberg, Argyris-Wittek, and there was a series of 3 papers by Guyot and Witten, in total 300 pages, so it's pretty hard to read. And there are a few papers I wrote with many friends of mine, and there was some paper by Jack and his students. And so I'm going to start describing the situation in a stringy language, and I'm going to gradually make it more and more precise in a mathematical sense. So I guess string theorists in the audience will understand less and less as my talk proceeds. And hopefully, mathematicians in the audience will understand more and more as the talk proceeds. OK, so let me start. So in early 2009, Davide Gaiotto came up with a great idea. I really think European culture is very strange. I mean, why this is OK and not representative Wiener? Anyway. OK. So his idea was the following. Wrap a 6-dimensional n equals 2, 0 theory of type G on a Riemann surface with lots of punctures. And this gives a 4D n equals 2 theory, depending on the complex structure of C and the type of punctures of C. So these first 2 sentences were known for quite some time, for 10 years or a bit more than that. And the crucial idea by Davide was that the 4D n equals 2 theory obtained this way decomposes in a very nice way when the Riemann surface on which this 6D theory is compactified is split into 2 by pinching off a cycle. So this is the main physics point pointed out by Davide. And mathematically speaking, this should mean, I mean, I used lots of undefined words in this first slide. So mathematically, this should mean that there should be a functor, fg, for g, some simply laced Lie algebra or Lie group, from the category of Riemann surfaces to the category of 4D n equals 2 theories. So the idea is that you can associate a mathematical object, which I would call 4D n equals 2 theory, to a punctured Riemann surface. So this is one example of 4D n equals 2 theory by applying this functor fg to this almost pinching Riemann surface. And what Davide pointed out, was that if this connecting tube between the 2 Riemann surfaces is very thin and long, then this n equals 2 theory in 4 dimensions can be represented as a coupled theory constructed from the 4D theory associated to this Riemann surface times the 4D theory associated to this side of the Riemann surface, coupled together with the gauge group G, so this is how the data of the gauge group enter in the definition of the functor. And so this gauge group should have the coupling constant or the exponentiated complexified coupling constant Q. Yep. That's exactly the question you need to answer. So I'm going to slowly making things precise. At this stage, the problem is, I in fact prepared this slide. The problem is, in order to make this statement precise, I first need to define the object, which is the for the n equals 2 theory, and I need to define what I mean by the morphisms, etc., etc. But the formulation I would going to use is slightly different. I'm going to think about the groups, which are the flavor symmetries, as the objects, and consider the 4D n equals 2 theories as the morphisms between the groups. That will nicely make these things into a TQFT.
What gauge in this picture is
Yep.
probably just some subgroup of G.
In general, yeah, but I'm assigning only the full punctures on the both sides.
Well, that's hard to tell.
Right. Well, I said I'm going to start very vaguely and slowly going to make it precise. So thank you for the question. So the that will be the final goal, right, of this business. But what I'm going to try to do today is to try to extract something something which can be formulated rigorously out of this vague idea and try to convince you all to work on it. So it's not working yet, but I'm trying. This is because, OK, let me go back to this nice naked picture of Davide. And so the idea is to get 4D theory by wrapping, starting from 6D theory, compactified on a 2D surface. And then because 4 is 6 minus 2, you get 4D theory. But somehow it is known that there's only ADE type 6-dimensional 2, 0 theory. This is because one way to construct 6-dimensional 2, 0 theory is to compactify 10-dimensional type 2B string on some hyperkähler singularity. And there's only ADE type hyperkähler singularity with real 4 dimensions. That's why we believe that there's only ADE type and not the non-simply laced cases. Thank you for the question. So we believe that there will be, once we define what we mean by 4D n equals 2 theories, categories of 4D n equals 2 theories, there will be this functor fg for each choice of g, which is a simply laced Lie algebras, or the ADE type. Right. So I'd like to extract something simpler out of this very complicated but rich functor. So I'd like to make an analogy first. So consider a Riemannian manifold whose definition is rather complicated. We all remember when we were beginning undergrad student, right? And given a Riemannian manifold, we can extract a simpler mathematical object by various means. For example, you can just obtain an integer by taking its dimension, or you can just get the volume, which is a real number, or you can choose an abelian group, and you can calculate the cohomology ring with that coefficient. And these objects are naturally associated to this manifold M. And depending on the type of an object, cohomology or dimension or volume, they depend on various amount of information on the original mathematical object. For example, volume depends on the metric on the Riemann surface, sorry, the Riemannian manifold, but the dimension or cohomology doesn't depend on the metric. So it only depends on the more, on the rougher aspects only. So similarly, so please imagine, please suppose that we already have a mathematical definition of this object T, which is a 4D n equals 2 conformal theory. Then we can associate various simpler objects by performing a certain operation. So one operation is to choose a 4 manifold on which to put this 4-dimensional theory, and you can calculate something called partition function. So this partition function associates to a pair of the theory and on the 4 manifold on which the theory is compactified, and it assigns a number, a complex number. You can also consider for this n equals 2 theory something called Coulomb branch, which is naturally something called special Kähler manifold. You can also extract a nice hyperkähler manifold by taking the what is known as Higgs branch to physicists from this n equals 2 theory T. And just as in the case of the Riemannian manifold, some of them depend only on a rough structure, and some others depend on a more detailed structure of the manifold. These Z or Coulomb branch or the Higgs branch depend on various amount of information inside this T. For example, this Coulomb branch as a complex manifold doesn't depend on the coupling, something called coupling constant in this manifold T, but the Kähler metric on this Coulomb branch depends on the coupling constant. This Higgs branch of this n equals 2 theory doesn't depend on the coupling constant. The behavior of this Z, the partition function on X, depends on X. For example, if you choose X to be S4, then this partition function depends on the coupling constant of this n equals 2 theory. But if, for example, if you choose X to be S3 times S1, it is known that the resulting complex number doesn't depend on this something called the number called coupling constant of this gauge theory. So you can extract various types of simpler objects out of this very, very complicated yet to be defined mathematical object. So the idea is to compose the Gayotto functor Fg, which sends a Riemann surface to a 4D n equals 2 theory with one of these operations. Then you can obtain a very simple mathematical object associated to a Riemann surface. So let's, for example, use this operation, which associates a complex number, or better phrased vector space to this Riemann n equals 2 theory. So if you consider this almost pinching Riemann surface and apply this Gayotto functor to get a 4D n equals 2 theory, and then apply this Z comma S4 to this, you get a complex number. But it is known how to calculate the resulting Z partition function from the partition function of the individual object. So because this n equals 2 theory is obtained by this n equals 2 theory and the other n equals 2 theory coupled together with gauge group is coupling constant Q, well, this is not exactly correct, but this is supposed to give you the idea how to compute this ZF of combined theory from ZF of the individual theories. So what you have is that I need to specify a number or a set of numbers or vectors associated to this extra punctures which appear after the pinching. And then these Z on this side and the Z on the other side are both functions of X. So you need to multiply the two functions on X and multiply by this Gaussian factor, and you need to integrate over this space X. So this is the way to get ZF of this combined Riemann surface from ZF of the individual Riemann surfaces. And therefore, almost by construction, this combined functor ZFZ sends a Riemann surface to a vector space. So you can almost automatically check that the resulting thing satisfies the axioms of 2D conformal field theory. And so we should have some conformal field theory representing this combined functor ZFG gamma S4. So this is the essence of some correspondence I cannot name. And so for example, if you start when capital G is SU2, the resulting CFT is known to be the Liouville theory. And in general, for general G, the resulting 2D conformal field theory is believed to be the Toda theory of type G. So that's one example of extracting a simpler object out of this very rich functor f of G. But I'd like to extract even simpler object because, well, I don't know which is simpler, but the axioms of 2D CFT is pretty complicated, and also it depends on this gluing parameter, the length of the tube, Q. So I'd like to really extract something which doesn't depend on Q at all.
Can you say what X really is? Is it the chi-squared representation of G, or?
X is a element of Cartan of G. Yes. So you need to integrate over rank G elements. Yes. So instead, I'm going to compose the Gayotto functor with the Higgs branch functor. So Higgs branch is a hyperkähler manifold naturally associated to any 4D n equals 2 theory. Therefore, if you compose these two operations, it naturally associates to a Riemann surface, a hyperkähler manifold. So the hyperkähler manifold associated to this combined Riemann surface is known to be given by the product of the Higgs branches associated to the n equals 2 theory associated to each of the Riemann surfaces divided in the sense of hyperkähler quotient. And this is known to be independent of Q in a favorable cases. And therefore, one subtlety pointed out to me last week by Greg is that it's not really quite independent of gluing parameter Q if you consider the resulting thing as hyperkähler manifold. But in the holomorphic symplectic category, they are indeed independent of Q. So for the purpose of today's talk, I'm going to consider the resulting manifold as holomorphic symplectic varieties. So this combined operation Higgs Fg, which from now on I abbreviate by eta g, is a functor from the category of two cobordisms to the category of holomorphic symplectic varieties. So this is, in some sense, a topological quantum field theory taking values in holomorphic symplectic manifolds. So yesterday, we heard a very beautiful talk by Dan Fried about the definition of the TQFT and such. So I don't think I have to tell you about the definitions. But so in the usual TQFT, what is associated to Bordism is a map, linear map between tensor products of vector spaces. Here, we are going to associate a holomorphic symplectic varieties to the Riemann surface. So eta g is a 2D TQFT valued in holomorphic symplectic varieties. And the rest of the talk is spent in describing what is known about eta g we learned by stringy or M theory analysis. Yep. Yes, I'm going to give the definitions right now. Yeah. So this is the middle point of the talk. So So before going into the definitions and the axioms, let me warn you about one thing. One common way to associate a holomorphic simplex manifold or hyperkähler manifold to a punctured Riemann surface with some extra data is to consider the moduli space of the Hitchin system with extra data associated with various punctures. But eta g is not that. In fact, you can think of this moduli space of the Hitchin system associated with the Riemann surface as one of the results of this composition of some operation to the Gayotto functor. In fact, if you compose something called 3D Coulomb branch operation to the Gayotto functor, you get this moduli space of the Hitchin system. However, this eta g is not this. In the physics language, what I'm going to tell you, this eta g is a 3D mirror of the Hitchin moduli functor. And in some sense, this should be morally dual to the Hitchin system, or symplectic dual of this Hitchin system moduli space. So let me go on. Let me start the definitions. So in the definition of TQFT, you need to define the source category. Well, the source category is always the same, and then the target category. So the source category is the category of two Bordisms. So the objects are just one-dimensional manifolds. So in this case, it's just collections of S1s in practice. And morphisms between two one-dimensional manifolds are just the cobordism. So for example, between S1 times S1 and S1, you can consider a pair of pants like this. And morphisms, cobordisms satisfy various interesting properties. Like if you have three S1s, then you can first merge the two circles, and then you can merge the third one. And this should be equivalent with first merging the last two, and then merging the first one next. So these can be called associativity in the source category. The target category is the category of affine holomorphic symplectic varieties with Hamiltonian group action. Objects are just semi-simple algebraic groups. I think I can use reductive algebraic groups, but for simplicity, let me just keep it semi-simple. Unit object is the trivial group, just identity. And the multiplication of two objects is just a Cartesian product. So if you have SLN and SLM, the product of the two objects is just SLN times SLM. Very simple. The Hom between G and G prime, two groups, is given by the set of, so the element of this Hom is an affine holomorphic symplectic varieties with a Hamiltonian action of G times G prime. And you need a certain extra condition of having a nice C star action, which rescales the holomorphic symplectic form. But for today, you can, for the moment, forget about it. So the typical example of such an affine holomorphic symplectic varieties is the cotangent bundle to any complex manifold, or quiver varieties in the sense of Nakajima, or just symplectic vector spaces with group action. So I'm assuming that there's a Hamiltonian or moment maps associated to this action of G times G prime. For two Homs, X and Y, I define the product between the product objects to be just a Cartesian product. So suppose X has G times G prime Hamiltonian action, and Y having H times H prime Hamiltonian action. Of course, X times the Y has the Hamiltonian action of G times G prime times H prime times H prime. So it's very simple. So the only non-trivial thing is the composition of the morphisms. So given x, which is a hom between g prime and g, and y, which is a hom between g and g double prime, I define their composition yx, which should be in the hom of g prime, g double prime, to be the holomorphic symplectic quotient of x and y with respect to the diagonal g action on which you connect the two. So, well, it's very easy to define. Yx is given by the subset of x times y on which the Hamiltonian, the moment map of this g action agrees, and you need to divide by the group G. In the notation of today's talk, G is really complexified group in the physics terminology. So you should think of this G as SLN or something like that. So these are the definitions of the objects and the morphisms. Let me summarize it again. Objects are just groups, and morphisms are affine holomorphic symplectic varieties with group action, with Hamiltonian action, and the composition is the holomorphic symplectic quotient. This makes it into a symmetric monoidal category, whose definition I learned last week. So we defined the source category, and we defined the target category. Oh, sorry. And eta g is going to be a functor between the two. And there is a nice identity in this hom, g comma g, which is the cotangent bundle to the group itself. So T star g can be naturally identified using left invariant form or right invariant form as g times its Lie algebra. And so you can take a typical element here is group element g and Lie algebra element x. So the Hamiltonian of this right action is you can calculate easily an x itself. Therefore, if you multiply this T star g with anything with g action in the holomorphic symplectic sense, then by definition, this is the subset of g x y in capital G times German g times y, in which the Hamiltonian of this side, T star g, is Hamiltonian of the y side, and you need to divide by g. So this just sets x to be mu of y, and you just remove the first small g, so it just becomes y. So T star g is an identity in hom g comma g. So this is why I needed to choose the holomorphic symplectic category to make it a TQFT. If you take T star g as a hyperkähler manifold, where there's a natural hyperkähler metric on T star g constructed by Kronheimer, in that case, T star g is not really an identity. It changes the hyperkähler metric of y in a rather trivial way, but it's not really an identity. For example, it changes the radius.
How did you get the direction?
I don't have any direction at all.
So your morphisms can be viewed as morphisms from G to G prime or from G prime
Yes,
to G.
yes.
There is no,
Yeah,
the composition
yeah.
also works complex.
Yes, yes. So it's a very trivial type of TQFT in some sense. Pardon? Sorry, sorry, I don't quite get the yeah, please teach me later. Yeah, I'm really learning the language. Sorry about that. So this is not really an identity in the hyperkähler category. That's what I wanted to say. So instead, we can assign an area as an extra parameter, extra data in the cobordisms. So I can consider the aread cobordism category, where area adds up. Then you can make it a functor in the hyperkähler category. But I'd like to really talk about TQFT here. So I consider the resulting manifold as holomorphic symplectic varieties. So this functor eta g is from the category of two Bordisms to the category of holomorphic symplectic varieties with Hamiltonian action I just defined. So what are the properties? As for objects, we have, because it's a 2D TQFT, you just have to assign something to S1. And I just assign this G itself to this S1. This is how this G, subscript G, enters. So this was easy. The fun is in the morphisms. So two general properties are these. So the identity between the two S1s is the object I just told you, T star G. And this capping off of S1 to nothing is well, it's basically a cotangent manifold to a homogeneous space. But for our purposes, it's more natural to define it as a subspace of T star G, where this second component is restricted on to the Slodowee slice associated with the nilpotent element, regular nilpotent element. So the Slodowee slice at the nilpotent element nu is a certain affine subspace of the Lie algebra G of the form nu plus V, where V is annihilated by, well, nu star, where nu star is defined so that nu star and commutator of nu and nu star should generate SL2 action in it. So it's the standard definition of the Slodowee slice at general nilpotent element n. But in this case, here I choose a particular nilpotent element n, which is the biggest nilpotent element, or regular nilpotent element. So this is the this is the assignment of these two. So in order to get a TQFT, I need to assign something to three-boundaried sphere. The problem is that it's not known in general. That's why I'm giving this talk here. I'd like to ask all of you to think about how to get this TG, but the physical principle tells us that there should be definitely some affine holomorphic symplectic varieties with 3G action with the marvelous properties which I'm going to talk about. So by the definition of the functors, this TG, I'm going to abbreviate this eta G of the pair of pants as TG. So this TG should have 3G actions corresponding to the three boundaries. So I call it alpha 1, alpha 2, and alpha 3. And because there is an action of mapping class group on this Riemann surface exchanging three boundaries, there should be also an action of permutation group of three elements which preserve holomorphic symplectic form acting on this TG, which exchanges these three G actions, so that doing alpha I and then sigma should be equivalent to doing sigma on TG and then alpha of sigma I. So this is part of the axioms of TQ.
What happens with the remaining part of the Frey group? What happens with the pure Frey group? Why are you acting only by the finite clause of the number?
They are symmetric.
No, I understand that the symmetric group should act, but there is also a kernel from the mapping class that the map the symmetric group has a kernel.
Yeah, but this is supposed to be a symmetric category. There's no braiding operation. So the dimension, we know the dimension of this TG. That can be calculated from brain construction, whatever that means. But you can also calculate its dimension easily by requiring that capping off this three-punctured sphere. So this is TG, right? But you can easily cap off this part to get identity. And we know the dimension here, and we know the dimension there. So we know the dimension this here. Because when you do the hyperkähler quotient, so it's holomorphic symplectic quotient, the action is effective. So the dimension is really easy to calculate. And this should be the dimension. So at least for G equals A1, we know what they are. And we know that they really satisfy the axioms of TQFT. So for A1 case, this TA1 is just the tensor product of 3 copies of C2. So there should be 3 SL2 actions. So each of SL2 actions just act on each factors. And of course, it's very easy to see that these 3 SL2s act in a symmetric way on this flat symplectic space. The only non-trivial point in the definition, to check the axioms, is the associativity. So you can construct this 4-boundaried sphere in 2 ways out of a 3-punctured sphere. And you can glue this way or either the other way. These two look the same by rotating 90 degrees. But the important point is that you need to keep the group action. So I colored the boundaries so that you can distinguish them. So this means that the holomorphic symplectic quotient obtained this way, the action of this SL2 and the other SL2 acting on this holomorphic symplectic quotient should be the same with the action of SL2 here times SL2 there acting on this holomorphic quotient. Pardon? Oh, you want to check this? This rank G is 1, right? N is 1. Oh, it's wrong. No, it should be. What did I? Yeah, should be even. Yes. I guess it should be 6 times. Six times. So sorry, I think this is a trivial typo. Sorry about that, because this is dimension 8, right? Yeah. Sorry. Sorry about that. So the associativity is not completely obvious. But in fact, it turns out that this hyperkähler quotient construction of this manifold is exactly the ADHM description of SO8 one-instanton moduli space. And SO8 has SU2 to the 4th subgroup. And these 4 SU2 subgroups are embedded in a symmetric way inside SO8. So that guarantees that there's a nice action of exchanging these 4 SU2 actions acting on this SO8 one-instanton moduli space. So you can really check that, at least for this case, the axioms are satisfied. So for G equals A1, that is OK. Let me go on to G equals A2. So in this case, it is known that this TG manifold is just a minimal nilpotent orbit of E6. So you might ask, how can you have something like E6 out of just considering SL3? What is going on is that in the group E6, there are special subgroup, maximal subgroup of the form SL3 to the cube, and they are embedded according to the extended Dynkin diagram. So these 3 SL3 actions are embedded in a natural way. And you can check that the dimension formula agrees once you correct the coefficient. But associativity is not checked yet. With Andy sitting here and Davide, we checked a slightly weaker version of associativity, but we haven't checked this associativity of 2 nilpotent orbits of E6. So please prove it. You just need finite amount of time. It's a very explicitly known varieties with explicit defining equations, and we know the moment maps, which are E6 group element. Embedding into the E6 Lie algebra itself. So you can perform the holomorphic symplectic quotient. Done. So that's what you need to do. For G other than A1 or A2, The known properties are not exactly directly for TG, but for a version of manifolds associated to Riemann surfaces with punctures which are labeled by ρ, which is a homomorphism from SL2 to G. So I need to slightly extend the source category by allowing punctures on the morphisms, I guess. So this part is not really. Yeah, yeah, but yeah, but I need to tell the audience what is the known thing about this manifold TG. So let me introduce this capping off to a puncture labeled by ρ. So this is associated. I associate a holomorphic simple manifold, which is a fibration over G of a generic Slowly slice at the general nilpotent element, which is associated with SL2 triple. So this is a representation of SL2. So E is mapped to a nilpotent element in the German G. So this is the Slowly slice. So you can always connect these things to this TG theory by performing this capping off procedure. So practically you take TG and you take three cotangent bundle of homogeneous spaces and perform the holomorphic symplectic reduction against G cubed. And I call this manifold TG of ρ1, ρ2, ρ3. This is a holomorphic symplectic varieties obtained by this Bielawski's slicing procedure. And for AN, when G is AN minus 1, ρ is a homomorphism from SL2 to SLn. Therefore, they are characterized by how the defining n-dimensional representation of SLn is decomposed into the irrep of SL2, which is naturally associated with a partition of n. So there are a few cases. The result becomes just symplectic vector spaces. So for example, if you take one puncture to be n minus 1 comma 1 and the other to be 1 1 1 1 1 1 1 1 1, then you get v times v tensor v star plus v dual tensor v, where v is just the fundamental representation of SUN. You can also choose this slightly funny combination of the punctures. You get this flat symplectic vector spaces where you have antisymmetric square of this defining representation and its dual, and some extra copies of defining representation and its dual. So you always have one vector space and its dual. So this is naturally symplectic vector spaces, and these are the known results. If you want to know more about various special cases, you can open up a paper by Jack sitting here. So, but it's written in a completely different way, so I'm afraid it's very difficult for mathematicians to get data out of that. But these are two data. But these are just simple cases. More surprising properties are that if you consider T of A 3k minus 1, KKK, 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 this is the framed centered K instanton moduli space of E6. So when K is 1, this is TA2 theory, which I already talked about. And so 1, 1, 1, 1, 1, 1, 1, 1, 1. And if you go back to the definition of this capping off procedure, for 1, 1, 1, this is T star G itself, because rho E is 0. So this is, in fact, just identity. So for rho equals 1, 1, 1, you don't do any capping. So this first object, when k is 1, is TA2, which I already talked about. So this should be the nilpotent orbit, or minimal nilpotent orbit of E6, which is, in fact, just the moduli space of one instanton of gauge group E6 with R4 part removed, which is always there in any instanton. in any kinds of instant homomoduli space. So similarly, you can consider TA for k minus 1 with this choice of slicing, and this should give k instanton moduli space of E7. Is there any question? It's an instantons on S4, yeah. And you need to add the framing at the north pole or south pole. Yeah. And if you take 6k, you get instanton moduli of E6. So these numbers encode the structure of the extended thinking diagram, as you have already guessed. Right? So for E6, because there are 3, 3, 3 lengths, that's why you have KKK, KKK, KKK. For E7, you have something like this is why you have 4, 4, and 2. And for E8 case, this is the extending diagram E8. That's why I associate this particular puncture to this particular slicing to this theory. So the way we get this information is by using lots of string dualities. But at least you can check that the dimension formula easily reproduces the expected dimension of the k instanton moduli space of these gauge groups. And also you can check the existence of the Hamiltonian actions, etc., etc. So that's basically it, or no? Yeah, that's basically it. So TG are very intriguing holomorphic symplectic varieties, which should satisfy this first of all associativity, and which can also give various interesting holomorphic symplectic varieties by capping off or slicing using this procedure. So that's basically it. So summarizing, the properties of the functor eta G from two Bordisms, categories of two Bordisms, to categories of holomorphic symplectic varieties are described. This is conjectural for when G is not equals to A1. For A2, I almost told you almost all the ingredients. So all you have to do is to check the associativity. So please do that. And in order for go further than that, you need to guess what is TG in general. And the full set of axioms and known properties, I mean, I guess it's very difficult to go on without any written down set of properties. So I'm going to provide axioms and known properties on the archive pretty soon. And if this talk hasn't convinced you yet, as a prize, I will offer you a nice dinner at a sushi restaurant in the IPMU. So please really think about it. Thank you very much. Yep. No.
It's kind of an obvious functor of the kind you wrote, like the surface. I can just look at the representation variety of the surface, which local systems on the surface with visualization on the function. So there is a functor from the category to that kind of G variety category.
Do they have the right group action?
It's an functor. I mean, it's basically some version of looking at rotation space of the function surface. But
is there an action of G to that?
Sure. Yeah, I mean, just by changing the visualization. And the gluing of surfaces is given by Hamiltonian reduction. Yeah, I mean, so there is an obvious functor that satisfies these properties. And you said in the beginning it's not this one, so I'm not. Well, you said this is not.
That's strange.
Well, there is the thing that gives you the three-dimensional Coulomb branch,
Right.
which is also a hyperkähler manifold, and
I mean, this
Because
is
they're
not
all
that.
dimension, doesn't it?
but it's different than that.
The dimension is not the dimension here.
Even the corrected version of the dimension.
You're the correct.
Does that space satisfy this?
Sure.
No, it'll satisfy all these properties. It won't have the dimension that you.
Well, but that
How are you going to get 6 times the dimension of the bottom point on the 3.2?
does it associate to annulus? Is it T star G?
Well, I mean, just looking at local systems on the cylinder, which is just a complexified group with, and, well, you look at systems would be that much of an obligation, and I would do two times visualizations. So it would be something like G mod G plus unit dimension.
Okay, so go down to the module.
Yeah.
Yeah. Other questions? Well, if everybody's got their homework, you two handed.